Volhard Zelinsky reaction, or the HVZ reaction. Carboxylic acids generally do not undergo substitution at the alpha carbon. Why? Because when you take a look into the structure, here we have the alpha hydrogen, here we have the hydrogen from the carboxylic acids. Now, between these two hydrogens, which one is more acidic? Obviously, the hydrogen from the carboxylic acid is going to be more acidic, and therefore, when you react it with a base, this is the hydrogen that will be abstracted. But you can still do the alpha substitution of carboxylic acid by converting that into acyl bromide, for which it has to be first treated with PBr3 and bromine, or you can also take phosphorus and bromine, which is also going to give us PBr3. Let's now take a look into the mechanism for the HVZ reaction. In the first step, the carboxylic acid is going to get converted into an acyl bromide, for which we are going to use PBr3. The PBr3 is going to convert this OH into a good leaving group, so the Br minus can go and attack the carbonyl carbon. Now, once this is converted into an acyl bromide, this acyl bromide is going to be in equilibrium with its enol tautomer. Here is the enol tautomer. This enol tautomer is going to make a nucleophilic attack on one of the electrophilic bromine atoms, for which these electrons are going to come in to form the double bond, and the carbon-carbon double bond is going to make a nucleophilic attack on this electrophilic bromine, thrust these electrons onto the other bromine atom. Now we can see that the alpha hydrogen has been replaced by a bromine atom. Now in the next step, water is going to deprotonate this hydrogen from the carbon and oxygen and neutralize that positive charge on oxygen. And this bromo-substituted acyl bromide will be hydrolyzed to the corresponding carboxylic acid. Water will act as a nucleophile, thrusting these electrons onto oxygen. Since you have a good leaving group here, as these electrons right here come in, the Br is going to leave. So basically this is a nucleophilic addition elimination reaction. And in the next step, this hydrogen right here will be deprotonated to give the alpha brominated carboxylic acid. So here is a final compound where you can see that the alpha hydrogen has been substituted for an halogen, and you still have the carboxylic acid functional group. The alpha halogenated carbonyl compounds are extremely useful in organic synthesis because they can be replaced by other nucleophiles. In the case of aldehydes and ketones, we can only use weak bases, because strong bases can create enolate ions. Say for example, here we do have alpha hydrogens, and in the presence of a strong base, one of these hydrogens could be abstracted, and therefore it could lead to the formation of an enolate ion. And that is the reason why we always needed to use weak bases in the case of aldehydes and ketones to replace the bromine at the alpha carbon. In the case of carboxylic acids, you can use both weak bases and as well as strong bases. Let's say that you're going to use a strong base. A strong base will first deprotonate the hydrogen from the carboxylic acid to create the carboxylate ion. If the strong base will go and abstract this hydrogen, this is going to put a negative charge on this carbon, creating a dinegative ion. But this dinegative ion is quite unstable. So because of which the strong base will go and replace this bromine and give us the product.